We're going live. Good afternoon and welcome to MAE 113 Calculus for the Liberal Arts. My name is Richard Kohar and this is Lecture 9, Product and Quotient Rules for Differentiation. Again, make sure that you type in the comments below saying, yep, you can hear me. Make sure that I don't start talking for 2 or 3 minutes and realize you all can't hear me. Perfect. Good. Excellent. So last time what we had done was we'd done the sum rule using derivatives, and then we had a combined power rule, and in the end we were able to do some longer polynomials and we could differentiate them. And so we had derived all of that, we had shown it had worked all using proofs, and so hopefully what we would like to be able to do now is look at say functions that have products in them or quotients, and it would be nice if we could come up with some differentiation rules. So the product rule, okay, well maybe I'll start with the sum. And in the sum rule, what we had is if we had two functions f and g, so that it's a plus, and we are going to differentiate that, or using Leibniz notation, I could write like this. That if I differentiate that, it's just f prime, or the derivative of f, plus the derivative of g. And in Leibniz notation, I can write that this is applied to each function. Or you could write it like df by dx plus dg by dx. And accordingly, like if you had a difference, it also works as well. Unfortunately, the product rule, it would be nice if I said, it would be nice if it worked the same way. So what I mean is if I had the function f times g, and I have it primed, or using our Leibniz notation, f times g, it would be nice if I could just do the derivative of that. So just applying the derivative to each individual function. But unfortunately, this is wrong. Oops, and it's so wrong, the ink wouldn't even let it dry on the page. It's wrong. And again, this is a very common mistake that happens. Unfortunately, it doesn't work out that way. So instead, it's a bit, yeah, I know, the ink. This lecture is brought to you by Waterman. It's actually a decent ink, but unfortunately, the paper that I'm using is not the best. The rule is if I have a function, I have f, and if I use like x for that, for the times g, Yeah, it works for limits, but it doesn't work for derivatives. Exactly. And it's weird why it doesn't work. So we're going to do the proof for it. The proof is not that difficult. There's one trick. Of course, there's always a trick involved in the proof, but the trick isn't, too difficult, and we'll see why. So we have f and g, and so it ends up being that it's the derivative of the first function times the second function, don't touch, plus the first function untouched multiplied by the second function with the derivative. So and just writing it again in Leibniz notation, you have df by dx times g plus f times, and that's, I'm just using a dot in this case. I mean, I can write a little cross there. dg by dx. So why doesn't it work like our limits? Well, let's do the proof for it. Because you have to see it to believe it. So what we're going to do is we're going to create kind of this function of functions. We're going to call this that f times g. We're going to call that h. Times. So I have f and g. And what I'm going to do is I'm going to take the derivative of that. So I have dh by dx, and using our definition of the definition of the derivative, which is the limit as delta x goes to 0 of h of x plus delta x minus h at x, all divided by delta x. So hopefully by the time that you're done this course, you should remember with the derivative, the definition of the derivative. Okay, and then what we do is we substitute in the x plus delta x into these. So if I substitute this in, the x becomes x plus delta x, so that's x plus delta x equals f sorry, I just looked up and I saw a question which is, for tests and quizzes, will we be asked to do the proof or simply just use the rules to apply the derivative? That is a good question. It's quite possible on a test that I could ask you that. And probably I will ask you for a proof on the test. Quizzes are hard, and the reason for that is because everyone doesn't know how to type math into the computer, and also it takes a really long time to type math into a computer. It's kind of longer than if you had written it. So when we're doing the quizzes through Moodle for 10 minutes, and it's all computer graded, I usually am looking for a final answer, or I'm testing some type of concept, or there's a visual component to it. So on the quizzes, no, there's not a way for me to test the proof, but what I'm going to say is you should know how to do it, and it will be on the test if it's not on the quizzes, and it will probably show up on the exam. Okay. Hopefully that answers the question. And the other thing too is getting used to, if you're in business or you're in economics, I mean, I always look at economists as mathematicians who are able to get a Nobel Prize. So you're going to have to do math, and math involves demonstrating or using proofs to show something is correct. So when you come up with a new formula or you derive something, you're going to have to show it. Okay, same thing with this one, H here. Now, for those that didn't know, yes, mathematics does not get a Nobel Prize. The reason for that was Nobel thought that mathematics had enough reputation that it didn't need to be elevated. So, but we do have something that's very cool in mathematics. So we don't have the Nobel Prize, but we have the Fields Medal, which is named after a mathematician, and that's usually awarded to somebody under the age of 40 who has made a very big contribution to their field or into their subject, and they have to be under 40. And that's only awarded every 4 years, kind of like the Olympics. So every 4 years we get to have, we get really excited. And okay, so the trick for this proof, I need to be able to separate this into two different functions, right? I want to, basically, I need to get the derivative of f and the derivative of g, right? Because I need to get it back to looking like df by dx. I need to get it to something like this. And same thing with dg by dx. So same thing. So what I want to do is, it would be nice to be able to group these somehow into something like that. So what is the trick that we're going to use? We're basically going to add 1 and minus 1. Now, I mean, we don't literally add and subtract the number 1. So let me just write this out again, because I think we're going to stick it in the middle here. I don't extend that line. So what I wanted to do is I'm going to minus f of x, gx plus delta x, plus f at x, gx plus delta x. So I've squeezed it in there. But essentially, this is the same. This here, f at x, gx plus delta x, and x plus gx plus delta x. So what I have here is the same term and the same term here, except I have a minus. So these cancel out. So I have minus 1 and 1, right? So that basically I've added 0. So I haven't changed the numerator. I've just kind of manipulated it. Okay, so what does that get us? Well, what does that get me? What I need to do now is I'm going to factor out this g here. So just looking at this part right here, looking at that part right there, I have this here. That's the same. So what I'm going to do is I'm going to factor that out. And I still have this ridiculously long line. Okay, so what I'm going to do is I'm going to factor out that g x plus delta x. I'm going to factor it out, and I'm going to put it over here. So I mean, I could put it at the beginning, or I could put it at the end, so I'm just choosing to put it at the end here. And then that means that for this term, I'm left with the x plus delta x minus f at x. Okay. Now I have this thing that I can look at here. Ooh, I'll switch to red. So I'm looking here. And what I notice here is I have an f at x and an f at x here. Let's pick sky blue. So I have an f at x here and I have an f at x here. So what I would like to do is I'm going to factor that out. So I'm going to pull it out in front here. And so what I'm left with is g x plus delta x minus g of x okay. Okay. What does that get me? Right, we're trying to get it to look something like that. Okay. Well, what I'm going to do now is I'm going to split these two up. I have a term here and I have a term here. Right, I have two terms. So I'm going to split them up into two or I can, yeah, I'm going to split them up into two at first. Let's see what that gets us. So this is by our sum rule of limits. And just writing this out again. Okay. What else? What else? Number 2. And then what I'm going to do again is I'm going to apply the product rule for limits. So here's the product rule. So from here, I'm splitting it up for this one and this one. So I'm going to have that, and I have that, times the limit as delta x goes to 0 of g of x plus delta x. So notice that I just shoved the delta x to the one part of the fraction. And I can do that, right? That, you know, for instance, maybe I won't write that on the proof here, but I have 3 times 4 divided by 2. That's equal to 3/2 times 4. So I can still do that, right? So I've just split it, and I've just assigned that delta x to this one. And I'm going to write the plus. So on this side here, I have 2 as well. So I have the limit as delta x goes to 0 of gx plus delta x minus g of x. Same thing. And split that up. Okay. Now we have this right here. We immediately recognize that that's our df. Okay. And I will leave this limit as delta x goes to 0. Plus, same thing here. I have the derivative, or the definition of the derivative for g here. So that is dg by dx Okay, so now that I have that, I have df by dx. And now for this one, there's nothing that can stop me from substituting in 0 into here, because I'm not dividing by 0, I'm not square rooting by 0. So it's all good. Like I don't have to worry about that. So I can actually let that delta x go to 0. So that's multiplied by g of x. Plus, now on this one, I have dg by dx. There's no delta x in here to worry about, so that's multiplied by f at x. And to get it to look like our rule that we had in front here, that's what we're trying to prove. Multiplication is commutative. We should remember that from 106. Multiplication is commutative. And what does commutative mean? The order does not matter. So again, I can write df by dx times g plus f of x dg by dx. So it is kind of weird that it doesn't follow like the sum rule where we can just apply the derivative to each individual function. In fact, it's like we have pairs. We have f and g, and the first one is the derivative, and the second function is the derivative in the second term. So, and you ask me, why is it like that? Well, the proof is in the pudding. We just did it. If you do it this way, it's going to be wrong. You're going to get the wrong derivative. So, there we go. Excellent. We did a proof. So what was, let me just summarize. What was the difficulty about this proof? The difficulty in this proof was adding and subtracting basically 1, so that we had 0. We added 0. The trick maybe is figuring out what kind of term that we should use that allows it to, that we could factor it out nicely so that we could break it up into those two individual definitions. Okay, so we have the proof of the product rule. Does the quotient rule work the same way as the product rule? No, it doesn't. It doesn't. It's a different rule altogether. But we will prove that. Not to worry. But before we move on to that, I mean, we have a new tool, so let's not. It's like we got a package from Amazon. We have to play with the toy first before we move on to the next toy. And really, I shouldn't call it a toy. It's a tool. It's, you know. But we love toys too, right? Something new and novel. So we have this new rule. Why not use it? So we're going to differentiate y equals, let's do x squared times x cubed plus 1. Okay. I know it's simple, but the reason for that is so we can do a check afterwards. Using the product rule, we're going to call this will be our f, and this will be our g. So if we do dy, okay, I appreciate a short answer at times, even if it's like an exception to an exception. The quotient rule. The quotient rule is, if I have a function, we're going to call it h, and I have f over x over g, then if I take the derivative of that, it's f prime of g minus f g at prime, all divided by g squared. And of course, we're going to prove it. There is a way of using the product rule to do. So this is a quotient rule. There is another way that you can use the product rule instead of using the quotient rule, but it requires us to use another rule as well. So that is okay. This is why I still miss classes, because there is instant feedback. So I can see faces, I can see heads nodding or confused looks. Okay, so our rule was dy by dx. So we have the derivative of the first function times g plus derivative of the second function, which is, or sorry, it's our first function we don't touch, times the derivative of the second function. So in this case, the derivative of f is, using our power rule, that becomes 2x times g, which is x cubed plus 1, plus, then we have our f function, which is x squared, times the derivative of g. So in this case, derivative of g, so I have x cubed, which is 3x squared, and the derivative of constant is 0, right? Rate of change of a constant is 0. Okay. Now what we can do is we can expand that out and we can simplify. So I have 2x to the fourth plus 2x plus, I have 3 times x to the fourth. Hopefully I've done that correctly. I have an x to the fourth and an x to the fourth. So what I'm going to do is I'm going to write it in ascending order. I have 2x, and I have 2 plus 3 gives me 5x to the fourth. So I think that's good, or, you know, it depends on certain textbooks. I can't factor out 2 and 5 are prime, so x can come out, and I'm just left with 2 plus 5x to the 3. Okay, so this is a fairly, I'm going to say, simple, and the reason for that is because we didn't necessarily have to use the product rule in this case. What we could have done is we could have expanded this out and then used our regular rules. So as part of our check, I'm just going to rewrite my y function. I can expand this out, so I get x to the fifth plus x squared. And then if I take the derivative of that, I get 5x to the fourth plus 2x. And then again, I can simplify, I can factor out an x, so I'm left with 5x to the 3 plus 2, or just swapping the order, because again, multiplication is commutative. So you can see that I get the same answer. So that's good. I have some confidence that I got the right answer. Now, some people may say that this was easier to do or this was easier to do. You'll find that when you're doing math in the real world, one way might be easier than the other. But this was for a very straightforward polynomial. So what other things can we come up with a more complex? Where did 2x come from? You'll have to, is it when I was doing this one right here? Like this 2x right here? Yes, exactly. 2x is the derivative of x squared. So that's what I've done here. So using our rule here, we have x to the fifth. And if I differentiate that, so if I call that y, and I take the derivative of that, the exponent comes down in front, so it becomes 5. I'm left with x, and the exponent drops down by 1. So it goes from 5 minus 1, or just down to 4. And similarly here. If I have x squared, taking the derivative of that, the 2 comes down in front, so I have 2x, and the exponent 2 drops down by 1, so it goes down from 2 to 1, and that's why I could write 1, but we assume it's 1, so we just write it as 2x. Does that answer your question, John? Okay. Now this is the product rule for two functions. What if we had three functions? What if we had three functions? We're definitely not going to do the product rule for three functions. We've already done it for two. That's good enough for us. We've established that. So what we can do instead is, if I have f times g times h, and I want to take the derivative of that, we do that same trick that we did last time when we were showing the sum product, or sorry, the sum rule for three functions. So I'm going to group two of these functions together and treat them like one. So I can take f and g, I'm going to group those together times h. And so the idea is it's applying the derivative to the first function and leaving the second function alone, plus the first function, and we apply the derivative to the second. So if you think about this, I have f and g, and it's the derivative is applied here, and then in the second case, it's applied there. So we're going to do the same thing. The derivative is applied to the first one, and we leave the second function alone, plus we leave the first function alone, and then multiply it by the derivative of the second function. And now, so that's by the product rule. And so we can do the same thing here. We write it down like our normal rule that we had up here. So we've already done it. So in that case, my h, so it's the derivative of the first times the second unchanged plus the first function times the derivative. And this is all being multiplied by h, so expanding that out. So that's by the product rule. So I've just expanded out my h here, and then I'm left with the f, g, h prime here. So if you have three functions, basically you have f, g, h, and it's three times here, and it's on the first term, it's the derivative of the first function. On the second term, it's the derivative of the second function. On the third term, it's the derivative of the third function. So you can see it's moving. My box is moving to each function on each term. So again, first term, first function's derivative. Second term is the second function derivative. The third term is the third function derivative. And that can also work for n functions. So by repeatedly applying your rule, you can get for n functions. Okay. So here's 3. Let's do the quotient rule. So the quotient rule is, if I have f and g prime, then it's the derivative of the top function times the bottom function minus the top function multiplied by the derivative of the bottom function, all divided by the bottom function squared. And in Leibniz's notation, I have d by dx of f of x divided by g of x so again, it's the derivative of the top function times the bottom function minus the top function times the derivative of the bottom function, all divided by the bottom function squared. Oh yes, and what's important about this? This is also assuming that g of x is not equal to 0. Right? Again, we can't have an undefined function in the denominator. We can't have it making it go to 0, and let's do this proof. Oh yeah, this is nice. Why is it nice? Because we're not going to use limits. So hurrah if you didn't like it. Because, again, we've already proved the product rule, which means that we can use it. And that's what we're going to do. So what we're going to do is we're going to call this f and g, we're going to call that like h. So we're going to, this is a quotient of differentiable functions. Okay, which means that I have h of x is equal to, I'm just rewriting the function again, and what I'm going to do is I'm going to rearrange it so that I have, I'm going to bring this g function to the left hand side, so I have h of x times g of x is equal to f of x. Okay, I'm just going to flip it so that it makes it easier to write. Okay, so we've assumed that these are a quotient of differentiable functions. So f is differentiable, g is differentiable, and Moreover, assume h itself is differentiable. So again, we're assuming that h, f, and g are differentiable, which should be good. Then, with this function that we have right up here, so we have f of x equals h of x times g of x. We're going to apply the product rule. So, of derivatives. So applying the product rule, I have h prime of x, g of x, plus h of x, g prime of x. So in the first term, it's the first function's derivative. In the second term, it's the second function's derivative. Okay. Then isolate h prime of x on one side of the equation. So taking that, what I'm going to do is let's see. How I would like to have, okay, so what I'm going to do is I'm going to have this x prime minus h of x, g prime of x is equal to h prime of x, g of x. Okay. And then what I'm going to do is divide the g of x so that that cancels. And so I'm left with h prime of x is equal to f prime of x minus h of x, g prime of x, all divided by g of x. Okay, so I'm not going to do any magic here. And by magic, I mean I'm just going to, well, use a new piece of paper here because I'm running out of room. And what I'm going to do is I'm just going to write h prime of x over on the left-hand side. And I have f prime of x minus h of x, g prime of x, all divided by g of x. So we're almost done. That h of x here, that's f over g. So I'm going to replace that f over x, g of x, times g prime of x, divided by g of x. And what I'm going to do is multiply the top and bottom by g of x. So I got g of x here. So again, I'm multiplying by 1, essentially. Okay, and now, again, this is being applied to each individual term. So I get f prime of x, g of x, minus, I have a f of x, okay, I'll leave that term here, times g of x times g prime of x, all divided by And in the denominator, I have it g times g, so that's g squared. This cancels. And just writing it out. And done. Time. I made it within the minute. So that is the quotient rule proof. So in this case, I didn't need to rely on using the definition of the derivative. In this case, what I was able to do was, using my previous rule, I was able to show that I could differentiate it using the rule, the product rule that we had previously derived, and came up with what we were expecting. So in this case, the derivative of f times g minus f times the derivative of g, all divided by g squared. And on that bombshell, thank you everyone for tuning in. If you have any questions, feel free to send me an email. We have office hours starting at 1 p.m., so in like about 10 minutes. So feel free to drop by if you have questions about the assignment. The assignment is now posted online on Moodle. These lecture notes will be provided PDF scanned and posted to Moodle. So make sure you check them out. Read them if you so choose, or if you didn't quite understand some of the proof, just go back and play it again, and also try it yourself to see how far you get through it, and maybe you get stuck. Check the video a little bit, maybe get a hint. But again, there's always a little tidbit in the proof that kind of makes it work. So I will catch you all on Monday. Enjoy your weekend, and have a good day.